Hello and good day, geometry. We will be going over CO27, which is an introduction to a perpendicular bisector. Now, we know what the word perpendicular means, right? Intersecting at a 90-degree angle. We know what bisector means. It means to divide into two equal sections. And so a perpendicular bisector is a segment, ray, or line that intersects a segment that intersects a segment at a 90-degree angle. That's the perpendicular piece. Sorry, I had a vision of what I wanted this definition to be, and then blanked when I got up here to write it. So I'm trying to remember what it was. And at the segment's midpoint. Okay, it is a segment, ray, or line that intersects a segment at a 90-degree angle and at the segment's midpoint. Two conditions for a perpendicular bisector. So let's draw one here for the perpendicular bisector theorem. Okay? I'm going to draw a segment in black because there's really nothing that interesting about a segment, so we don't need to colorize it here. So we have a segment, AB. Okay? And now I'm going to draw in a perpendicular bisector. And I'm going to draw it in green because green is going to represent what we know. Okay? We know that this is a perpendicular bisector. Right? We'll call this point C, we'll call this point D, and we'll call this down here point E. And this could be a segment, array, or a line. So you might have arrows on each end. You might have arrows on just one end or no arrows at all. Okay. What it intersects has to be a segment, though. Like AB has to be a segment because when we know it's a perpendicular bisector, meaning that AD is congruent to BD, and we have a right angle here, right? The right angle is that 90-degree intersection. And then the fact that D is the midpoint of AB, which is where this perpendicular bisector has to intersect, tells us that AD is congruent to DB. What we can conclude is that any point on this perpendicular bisector, I'll use point C here, in red is what we can conclude, any point on the perpendicular bisector is equidistant from the endpoints of the segment. Okay? So this is what that perpendicular bisector tells us. Knowing that we have a perpendicular bisector that I drew in there, CE, our conclusion is that any point on that bisector, I used point C, is equidistant from the endpoints of the segment. So we know that CA is congruent to CB. If I made another point on here, I'll do it down here. E looks to be about the same distance away as C, so I'll pick another one. I'll use point F here. Okay. Point F, being on the perpendicular bisector as well, we would know that FB is congruent to FA. Right? Any point on that bisector will be equidistant from the endpoints of the segment. That's what the perpendicular bisector theorem tells us. And again, we can use this going in knowing that the perpendicular bisector exists. So the converse of this theorem, which is 5.3, this tells us, again, we've got a segment here. I wasn't going to scroll this, well, no, yeah. We'll clear the ink, we'll scroll it down. Okay. The converse tells us that, again, if we have a segment, I'll use AB again. Okay. And I'll draw in green what we know. I'll draw in red what we can conclude. So in this case, the segment that I'm going to draw through here is going to be in black because right now there's nothing special about it. okay? But if we know that point C is equidistant from the endpoints of the segment, you'll kind of notice this is now the opposite of what we knew and could conclude in Theorem 5.1, because this is the converse. This is just the other way around. If we know that point C is equidistant from the endpoints of segment AB, we can then conclude, so this is going to be in red now, we can then conclude that not only does this intersect at a right angle, but that this point is the midpoint of segment AB, which means that A, we'll call M for midpoint here, AM is congruent to MB. Okay, so it works both ways. In the first one, in green, was the perpendicular bisector with the midpoint and the right angle labeled. In red was that any point on the segment is going to be equidistant from the endpoints of segment AB. In Theorem 5.2, it's just the opposite. If we're given that point C is equidistant from points A and B, we can conclude that that segment, ray, or line is a perpendicular bisector. All right? I'm sorry, 5.3. Converse is 5.3. The first one was 5.2. The point of concurrency. The point of concurrency. This is where. Do I want to scroll down here? No. The point where 3 or more segments, rays, or lines intersect. Point of concurrency, the point where 3 or more segments, rays, or line intersect. So if you only have 2 of them, okay, that point is just an intersection. You got a third one. All right, now it's a party. Now it's a point of concurrency. Okay, so point of concurrency is where 3 or more segments, rays, or lines intersect. The circumcenter is the name given to the point of concurrency of 3 perpendicular bisectors. So not only is it special enough to be called a point of concurrency, but if that point of concurrency involves 3 perpendicular bisectors, it gets its own special name beyond that. That is the circumcenter. And if it's got a special name, there must be something special about it. And thus we have Theorem 5.4, which is the concurrency of perpendicular bisectors of a triangle. Okay? This is where, if you've got a triangle, so we'll draw one out here. Try not to make it isosceles or anything. Kind of extend that out a little bit further there. Okay. The 3 perpendicular bisectors of that triangle will intersect at a point called the circumcenter. So, drawing 3 perpendicular bisectors, we aren't going to use the compass to construct it, especially being virtual here. So it's going to be a little bit of eyeballing here. But what you want to do is you want to do your best from each line, find the midpoint. So maybe label those first. Midpoint right about there. Midpoint right about there. Midpoint right about there. Okay. And then you're going to want to draw segments coming out at, as best you can, a 90-degree angle. So not going to be, connecting going straight across, coming out at a 90-degree angle. Looks pretty close. This one's obviously going to go straight up. And once you get 2 of them, then you can kind of make sure your third one intersects them both, okay, whether or not it's a perfect 90-degree angle. But this point right here, right, that is called the circumcenter, where the 3 perpendicular bisectors intersected. The point of concurrency, the circumcenter. And what's special about the circumcenter is if you draw segments from this point to the angles of each triangle, all three angles, those segments will be congruent. It's a lot of markings here, okay? It's a lot of markings here, but the three perpendicular bisectors of a triangle will intersect at a point called the circumcenter, and from that point, segments to the three angles of the triangle will all be congruent. Okay? So why would this matter here? You know, let's say that the cities of Champlin and Osseo and what else is around here? Brooklyn Center, okay, all wanted to commemorate their trifecta union with a statue that's equidistant from each town's city hall, right? So you've got Champlin City Hall up at the top, Osseo City Hall down on the right, and Brooklyn Center City Hall down on the left. And so what you would do here to figure out, you know, where's the statue going to be located so it's equidistant from all three town city halls, is you would connect each of them with a triangle, right? And find the circumcenter. And I'm just going to ballpark this one because I want to just isolate that circumcenter point without all the other lines in there. Let's just say, and this is close actually to an equilateral triangle, so the circumcenter is going to be close to the center here, okay? But that circumcenter point being equidistant from all three town city halls, which represent the angles of this triangle, that's where you'd want to place the statue. Okay, if this was the same situation, here's Champlin City Hall, Osseo City Hall, Brooklyn Center's City Hall, in a triangle that's not so perfect, not so equilateral, you can see that our circumcenter is not in the middle of the triangle, but it's in the middle of those three city halls, those three angles. Okay, so that's where the value of the circumcenter comes in. I think that's it. That's it. All right. So you've got a Google quiz to take. If you want to look at some more definitions, more examples, this lesson came from Chapter 5, Section 2 in your book, if you happen to have that home with you. Otherwise, if you've got questions, want to talk more, hop in on Zoom from 1:30 to 3. I'll post the link. Same link for both algebra and geometry. We can just talk about whatever you want to talk about. Otherwise, complete the Google quiz for Wednesday, for tomorrow, and tomorrow we will learn about angle bisectors and all the properties that come along with them. So until then, have a great day, enjoy yourselves, don't forget to like and subscribe, and we'll talk to you later.